What happens when AI systems remember only what matters, learn to read the hidden thoughts behind user messages, and survive training crashes with near zero disruption? In this episode, we dive into 3 cutting-edge papers pushing AI forward from different angles: smarter on-device memory for personalized RAG, a groundbreaking dataset revealing the latent thoughts behind real human-AI conversations, and a tiered checkpointing system built to keep large language model training resilient. Together, they point to a future where AI is more personal, more transparent, and far more reliable. Let's explore the first paper, From Volume to Value Preference Aligned Memory Construction for On-Device RAG. This paper proposes EPIC, an on-device RAG memory construction framework that shifts personalization from storing all raw traces to storing only preference-relevant evidence. EPIC uses a 3-stage pipeline: semantic-based coarse filtering with contriever-style embeddings and cosine thresholding, preference-aligned fine verification with an LLM decision module and instruction generator, and preference-guided query steering that moves query embeddings toward the nearest preference vector before face retrieval. The key novelty is instruction-centric indexing. Each retained chunk is converted into a compact, preference-conditioned instruction item pair, so retrieval is guided by explicit usage directives rather than raw text. On 4 benchmarks, PrefWiki, PrefRQ, PrefELI5, and PrefEvil built from Wikipedia, Researchy Questions, Common Crawl, and LMSYS. Chat. 1M. EPIC improves preference following accuracy by 20.17 percentage points on average over the best baseline, including NV, Embed, V2, while reducing indexing memory by 2,404 times and retrieval latency by 33.33 times. In one on-device test on a Jetson Orin Nano 8GB, EPIC keeps memory under 1 MB and reaches 29.35 milliseconds per query, with steering adding only 0.18 milliseconds. Ablations show coarse filtering drives most of the memory reduction, fine verification is essential for accuracy, and query steering adds a further 0.78 to 4.03 percentage points without extra storage. Let's explore the second paper, ThoughtTrace Understanding User Thoughts in Real-World LLM Interactions. ThoughtTrace introduces the first large-scale dataset that pairs 1,058 real users' multi-turn human-AI conversations with 10,174 self-reported thought annotations, covering 2,155 conversations and 17,058 turns across 20 language models, including GPT-5, 4, Gemini 3.1 Pro Preview, Claude Opus 4.6, and open weight systems. The key novelty is that each turn is augmented with 2 latent cognition signals: reasons for sending a message and reactions to an assistant reply. Analysis shows these thoughts are not redundant with transcripts. LLM-based semantic coverage scores are only 3, 22/5 for reasons, and 2, 0/5 for reactions. And frontier models infer them poorly, with average semantic similarity of 2.93 for reasons and 2.54 for reactions. Thoughts are also highly structured. Reasons concentrate in task motivation and goal, 36.9%, task continuation, 21.4%, and context grounding and constraints, 13.1%, while reactions are dominated by explicit affirmation, 72.2%, but also expose dissatisfaction in content relevance, presentation style, and scope fit. Compared with WildChat and LMSYS, Chat 1M ThoughtTrace conversations are longer, with an 8-turn median versus 2, and 57% of user turns extend prior tasks. Downstream, adding thoughts boosts next user message prediction from 21.6 to 30.6 semantic similarity, a 41.7% relative gain, and thought-guided DPO rewrites on Qwen 3. 5.4b raise arena hard style-controlled win rate by 25.6% over the base model and 4.5% over message-guided rewrites, showing that explicit latent cognition data can improve both user modeling and alignment. Let's explore the third paper, tiered checkpointing for fault tolerance in large language model training. Tier check targets a concrete bottleneck in large language model training. Failures are not uniform, yet most checkpointing systems treat them as if they were. The paper shows that in production, LLM runs, GPU and node crashes dominate, while rack outages are rare but catastrophic, and proposes a 3-tier checkpoint hierarchy that matches that failure spectrum. Tier 1, keeps lightweight differential checkpoints in local volatile memory for software failures. Tier 2 asynchronously mirrors them to a physically adjacent peer node for single node failures. And Tier 3 migrates base checkpoints to remote persistent storage for rack-level recovery. The novelty is not just placement, but lifecycle control. TierCheck intercepts deep speed and PyTorch serialization to capture in-memory-based checkpoints with zero copy, compresses frequent differentials with adaptive INT8 quantization for small tensors, and threshold-based top K-style sparsification for large tensors, then replays recovery using a fused multi-step operator that processes batches of differential checkpoints in one pass. A watermark-driven global reclamation protocol prevents premature deletion until a base checkpoint is durably committed cluster-wide. On a 1.6 GPU A800 testbed, TierCheck cuts checkpointing overhead by 62, 8, 80, 2.7% versus CheckFrec, Gemini, and DataState's LLM, reduces checkpointing time to 3.1 to 3.2s, and speeds recovery by 3.6 to 6.9 times for software failures, 1.8 to 3.5 times for node failures, and 1.3 to 2.5 times even for rack failures. It also preserves convergence on GPT-2 124M trained on Wikitext 2 and scales to 40B parameter models without accuracy degradation. That's a wrap on today's AI paper highlights. Thanks for watching.